Okay, so if we take a look at this Zener diode here, now remember I said Zener diodes are meant to be installed reverse bias within the circuit. So I'm going to put that right there. So I'm saying reverse bias because I know that this is the negative, and I know that this is the positive, or I shouldn't say negative. That is the cathode, and this is the anode on the Zener diode. And during the positive cycle, so now during the positive cycle, I've got this positive coming through here, and Zener diodes want to be connected reverse bias for them to be able to conduct. So let's say that this is 10 volts coming in, and we'll say that this is Zener diode is a 5-volt diode, meaning that when it's installed as a voltage regulator, meaning when it's installed the way it's designed to be used, which is in reverse bias, it's going to drop 5 volts across it. When it's installed in a circuit and it is in forward bias to the circuit, it's just going to drop whatever its forward bias value is. So we'll call that forward bias 0.7 volts, just like any other rectifying diode. You've been measuring them somewhere around 0.5 to 0.7 volts for the silicon rectifiers. So now if we take a look at this during the positive cycle, this here is reverse bias, and that's what it wants. So it means the point from here to here, if that starts to conduct, is actually going to be 5 volts. And if I have this in parallel with that, this will be 5 volts. So I've taken 10 volts and I've regulated it so I get 5 volts out of this. So if I was to look at this, okay, there's my 5 volt there. And what's going to end up happening is it comes up and it gets to 5 volts and then it shuts off. And then it goes back down into its negative cycle. I'll try drawing that again because that wasn't very good. So it gets up here like this, and it's clipped like that at 5 volts, and then it goes back down during its negative cycle. So now this is negative. This is negative. It's actually going to only have a voltage drop of 0.7 volts. 0.7 volts. So it must mean that the voltage across here and here would be 0.7 volts. Because if this is in forward bias and it's going to conduct at 0.7 volts, then I've clipped this at 0.7 volts on this side, negative 0.7 volts. And then when it gets back to positive territory, it will go back up, and at 5 volts, it's going to conduct, and then it's going to stop conducting at 0.7 volts, and it sort of continues. So we end up with a waveform that sort of looks like this, which is called a positive clipper. So again, it's a positive clipper, but we call this more as like a voltage regulator or a transient reducing circuit, meaning that it's reducing the amount of noise. So why would we even want to do this? Well, the idea is that clipping circuits are used mainly to protect switching transistors. You have millions of them in your phone, and it protects the switching transistors primarily from transient reverse voltages. So these values that are in the peaks that are either noisy, unfiltered, or they're transient voltages, or their peaks or highs, to get rid of them because we don't need them, and they just cause these problems at an atomic level. So if we clip them at a voltage where it starts to already function, it already starts to get that device to function, then we don't need to keep this whole back end of the transient over here. So now let's take a look at something interesting. So we're regulating the voltage, aren't we? I mean, that's really what we're doing. We're regulating that voltage. And then, if the rest of the voltage, we've got, if this is conducting, we get 0.7. If it's in reverse bias, which is going to drop 5 volts, and we got 5 volts, so 5 and 0.7. But what's interesting is, let's take a look at what happens if we take two of them and we put them back to back like this. So I'm going to drop this one in here. So same deal. Let me just get rid of this mess here. Okay, So during its positive cycle, I pen out again. So during its positive cycle, I've got this positive pulse coming out, and we'll say that they're both Zener diodes or same thing, 5 volts. So then this is positive here, which means this is reverse bias, which means that during the positive cycle, this diode here, we'll call this Zener Diode 1, we'll call this Zener Diode 2. So during the when this positive pulse for Zener 1 is positive, which meaning it's reverse bias, this thing is going to conduct and it's going to drop 5 volts. And that would also mean that if that is reverse bias, this is forward bias. And in forward bias, this is going to drop 0.7 volts. So therefore, my output from here to here is going to be the sum of these two voltage drops, which is 5.7 volts. 5.7 volts. So let's draw that on the scope. So I've got, we'll say it's somewhere around there, 5.7 volts. So it goes up and it conducts like that and then back down. And then we say, okay, during the negative cycle, so now this is negative, I got negative, so this is a negative cycle coming in. When the Z1 is in its forward bias, meaning it's just going to drop its regular 0.7 volts, and this is going to be reverse bias, meaning it's going to drop its full 5 volts, I'm still left with the same thing, aren't I? 5.7, but it's a negative 5.7. So it's going to conduct in this region until it gets to 5.7. And then, so essentially what we're doing is we're clipping out this top portion here and this top portion here, leaving this band from here to here, 5.7 positive to 5.7 negative. So we've been able to regulate both sides of the voltage to get the exact value that we want. And that's important because if I was to say, well, I need exactly 5 volts, then, we'll figure out a value that's going to work for us. Now, thankfully, there's much easier ways of doing this. I can simply take an LM7805. So let's take my AC power supply here. There's my AC power supply, and I'm going to take my positive and go to there. And I'm going to take my negative and I'm going to go to this line here. I'll do that in gray so you can see that there. Okay. So now I've got my voltage here. And what I'm doing is I'm telling the chip I'm bringing in, let's say I'm bringing in 10 volts. So my output now, so if I was looking across my scope, so let's get the scope in here. There's my scope. So my scope is looking at this, and I'm going to hook up my, let's see, I got my white here, so I'm going to hook it, that would be the black of the wire of my scope, the black of my scope, showing in white or gray here. And then my red wire is going to go on the output of this here. And so what am I going to see? Well, I'm going to see exactly, essentially, whatever this voltage is set for. If this is a 12-volt Zener, if the Zener diode is a 12-volt Zener, then I'm going to see 12 volts. If the Zener diode is a 5-volt Zener, then I'm going to see 5 volts. And that's really important to understand because now we can regulate voltage very simply using a very simple concept, which is based on semiconductor materials and its ability or its conductance band.